The Casimir effect is a phenomenon which occurs when we consider the fluctuations, the quantum fluctuations of a certain field that we consider to be massless and a scalar field. So we have a massless scalar field, let's call it phi, of two variables x and t. So we assume that we are in a 1 plus 1 dimensional space. So we have one dimension of time and one dimension of space. And this field will propagate according to the wave equation. So it satisfies classically the wave equation, which can be written like this: dt phi, and in particular this is a second derivative, so we have dt squared phi minus dx squared phi equal to 0. So I'm assuming that the velocity with which the field propagates, or the wave propagates, is the velocity of light, and I will set it equal to 1. Otherwise here you have a factor of 1 over c squared, but since c is 1, this is the wave equation. So you might think of phi also as an electric field or a magnetic field. That's usually the application of the Casimir effect. We apply that to the electromagnetic field. But this kind of reasoning and the subsequent considerations are quite general, so they are independent of the nature of the field in principle. And there are also some attempts to generalize this to gravity. There have been some attempts to generalize the Casimir effect to gravity, but I will not get into those details because that's beyond the purpose of this lecture. Here I would just want to show you the mathematics that will lead us to the derivation of the Casimir effect without specifically saying that we are referring to the electromagnetic field. I'm assuming that we have this scalar field phi, which satisfies classically the wave equation, and since we have just one-dimensional space, it's as if we are in a one-dimensional world where we also have a dimension of time if you want. So I'm considering two plates, but you have to think that these plates, quote-unquote plates, are actually points because we are in a one-dimensional space. We have just one spatial dimension. Anyway, when I say plate, I try to be a little bit more general because this can be generalized also to other multidimensional spaces, in particular three-dimensional space, where you have indeed three dimensions and also one dimension of time. But anyway, here you have two plates, and the first one is located at x equal to 0. The second one is located at x equal to L. And by assumption, we consider the fact that the field phi 0t, so sometimes I might write the time variable first, so I can write it like this or I can write it like this. And I hope that there will be no ambiguities. But for now, we'll try to stick to this notation here, where I consider the first dimension as the spatial dimension, and then we have the time dimension. So phi 0t will be 0, and by assumption, the field phi will be 0 also at x equal to L. So there is a distance between these two plates, quote-unquote plates, which is given by L. Now, a general classical solution to the wave equation can be written quite simply in the following fashion: phi of xt is given by a superposition of waves, and I will write a superposition over n from minus infinity to plus infinity, and then here we have a coefficient a sub n, e to the minus I omega nt, plus b sub n, e to the plus I omega n t, and this multiplies the sine of omega n times x, where omega n is equal to pi, and then we have an absolute value of an integer, which is this integer here, divided by L. If you substitute omega n here, and you set either x equal to 0 or x equal to L, you can easily see that this sign will be 0. So the fact that we only have the sine and not the cosine is due to the fact that we have to apply the boundary conditions that I have written here. So this one here is also 0. You can check that these waves for a fixed frequency, where the frequency is omega sub n. So if we fix n, we have a certain frequency. So this would correspond to a sinusoidal function with a well-defined frequency. And also these terms here are sinusoidal in time. So we are fixing the frequency also in here. But anyway, you can show that each frequency, or in particular each of these terms, and I'm considering this as just one term, satisfies the wave equation there. It's quite simple, because when you take the second derivative with respect to t, here you will get a factor of I omega n squared, which is equal to minus I omega n squared, which is equal to minus omega n squared. On the other hand, when you take the second derivative with respect to space, from here you get a minus omega n squared from the sign. So you can see that this equation here is satisfied. It's quite simple to see that. Now, at this point, it is possible to promote this field to an operator, and similarly, we promote these two coefficients to operators. And let me also tell you that, for example, in this case, if phi is a real scalar field, you have also a relation which should be satisfied by an and bn, because you have to impose the fact that the imaginary part of this object here is 0, and that will give you a condition to be satisfied. So in this case, that's not important. Now, if we promote phi to an operator, I will call it phi hat of x and t, and I will rewrite the operators an and bn, but in a different fashion. So I will just rewrite the expression in a more convenient way. So I will put a factor of square root of 1 over L. Remember that L is the distance between the two plates. And then the sum will go from 1 to infinity. So instead of going from minus infinity to infinity, I will rewrite the summation from 1 to infinity. And in principle, that can be done, because you can see that when you go from minus infinity to minus 1, these two terms here are exactly the same, because we are considering only positive frequencies, and these terms are symmetric if we go from minus infinity to minus 1, and if we go from 1 to infinity, right? So we can also just sum from 1 to infinity and redefine these terms. It's quite intuitive, so we can do that. And also let me tell you that, for example, when n is equal to 0, you can see that omega 0 is 0 from there. So if omega 0 is 0, these two terms here are just equal to 1, but that's not really important. What's important is the fact that this sign is 0. So we don't have a constant term, and that's why we can start the summation at 1. So you can try to understand it by writing down the expressions and do your considerations as well, because that will help you understand it even better. But anyway, here I will rewrite it as, so the sign, let me put it here, sine of omega n x, it's simply this one, so that cannot be changed. I have to put it there. Then I will divide it by a square root of omega sub n, and that can be done, because as I said, we simply have to redefine these coefficients. That can be done. And then here, instead of writing the coefficients, I have to write the other, they will not be the same, but I have to be careful because they will have to be operators. So the first one will be defined as a hat minus sub n e to the minus I omega n t plus a hat plus sub n. So in principle, they are different. There is a relation between them if the field phi is Hermitian. So in particular, if phi dagger, which is the complex conjugate transpose, is equal to phi. But anyway, that's not what I need in this case. Here I have e to the plus I omega n t written like this. Now at this point, I want to find some commutation relations between these operators, and I will have to impose the commutation relation between the field and the momentum density. And the momentum density is simply defined as the derivative with respect to time of the field. So this can be defined as pi. So this will be a function of x and t, because this is a function of x and t. But first, so in order to do that, and before defining the momentum density, let me take this expression here, and let's multiply both sides of this equation by the sine of omega nx and integrate from 0 to L over x. So here I have phi hat of xt integral from 0 to L. If you multiply these quantities here, you can see that we have a summation, so we have an infinite number of terms by the sine of omega nx using the following formula. So in particular, a simple trigonometric integral of the kind integral from 0 to L sine of omega nx sine of omega m. So in principle, this index can be different because here we are summing over n, but this n is not the same as this n here because this n is fixed. So you integrate over x and you remember the fact that omega n is equal to n pi over L. So in this case, I don't need to put the absolute value because n is a positive quantity, as you can see here. Earlier, I had defined omega sub n like this, but in this case, I had to put the absolute value because we were considering also negative frequencies, and I want this omega sub n to be defined as a positive number or non-negative number. And in this case, it would be positive because it cannot be zero. So we are excluding the fact that n can be zero. So we can say that omega sub n is positive. Anyway, this integral, the result of this integral is simply equal to L over 2 Kronecker delta nm. And the same would be true if instead of the sines, we have cosines, written like this, for example. So by using this formula, we can carry out the integrals on the right, and what we get is the following. We have 1 over 2 square root of L divided by omega sub n. Then we have a hat minus sub n e to the minus I omega sub n t plus a hat plus sub n e to the plus I omega sub n t. Like this. Now at this point, we can consider this expression, this equation here, and we can take the derivative with respect to t on both sides. Remember that I defined the derivative of phi as pi, which is the momentum density. So this is just a generalization in field theory of momentum. So this is the momentum density because the field phi has the same role that position has in the usual Lagrange formalism. So here this will be an operator, so I put a hat, and let's change the variable x to x prime for convenience, and we still keep t here. So we have sine of omega n x prime dx prime, and what we have on the right is the time derivative of this expression. So we get I over 2 square root of L omega sub n minus a sub n hat minus e to the minus I omega n t. So this minus sign comes from taking the time derivative of this. Then we have plus a hat plus over n e to the I omega n t. So here we still have a plus. Now at this point what I'm going to do is I'm going to consider a commutator between this expression here and this expression here. So I want to write the commutator like this. So I have a commutator integral from 0 to L. So in this case the integral is still from 0 to L dx phi hat of xt sine of omega n x, and then here we have integral from 0 to L pi hat of x prime t sine of omega n x prime dx prime, like this. So in this case I put the differential first, but whatever. And of course this would be the commutator of between this object and this object here. If we take the commutator between this expression here and this expression here, that's quite simple, because the only terms that do not commute are this with this and this with this. So if you do the algebra, what you get is I L over 2 commutator between a minus n and a plus n, like this. For greater generality, if we put n prime here, we will get an n prime here. Here I'm imposing the fact that, for example, the commutator between a minus n and a minus n prime, even if n prime is not equal to n, this would be 0. And similarly, if we put a plus here and a plus here, so these two commutators are 0. The only non-zero commutator is when we have a hat minus and a hat plus. Now at this point, we impose the commutation relation between the field and the momentum density. In particular, the field phi of xt commutator with the pi of x prime t is given by I Dirac delta of x minus x prime. And I'm reasoning in units such that the reduced Planck constant is equal to 1. This commutator, by the way, appears when you consider the commutator of these integrals. So in particular, if you take these things into account, you can rewrite this quantity in the following fashion. You have an integral from 0 to L dx. You also have an integral from 0 to L over dx prime. Then you have I delta of x minus x prime coming from this equation. And then you have the sine of omega n x times the sine of omega n prime x prime. Now this point, if you remember this result, and the fact that for example, you can integrate over x prime first, so this delta will give you a factor of 1 when you integrate it, and you can set x prime equal to x here, because when you have a function multiplied by a Dirac delta, you can rewrite the same function evaluated at the point where the Dirac delta has its peak. And therefore here what you get is L over 2 times I delta n n prime. Therefore, the operators a minus and a plus are defined in such a way that the commutator between a minus n and a plus n prime gives us delta n n prime. So this is quite a simple relation, and they played the usual role of creation and annihilation operators. Now, at this point, we can also define the Hamiltonian density. So the Hamiltonian density is given by phi dot, phi hat dot if you want. So this would be an operator, if we replace the field with its operator version. So at this point, let me avoid writing the hat. So at the first, we do the calculation as if it is a classical theory, and then we generalize it to an operator. So in particular, here we have phi dot, the partial derivative of the Lagrangian density with respect to phi dot minus the Lagrangian density. And we have to define also the Lagrangian density. So remember that we started from the classical field equation, and the classical field equation is just the Klein-Gordon equation for a massless scalar field. So here we have L equal to 1/2 d mu phi, which is the Klein-Gordon Lagrangian for a massless scalar field, and this would just be equal to 1/2 phi dot squared minus, let's write it as phi sub x squared. So this is the derivative with respect to the spatial dimension. So for example, if we take the derivative with respect to phi dot, we just have phi dot from here, because the derivative of phi dot squared is 2 phi dot. So when we divide by 2, we just get a factor of phi dot. And therefore, we can see that the Hamiltonian density is just phi dot squared minus 1/2 phi dot squared minus phi sub x squared. So what we get is 1/2 phi dot squared plus phi sub x squared. And at this point, you can promote the Hamiltonian to an operator, the Hamiltonian density, and we can define the Hamiltonian simply as the integral over the spatial dimension. And when we integrate over x, we have to integrate from 0 to L. And then here we have the Hamiltonian density. So now let's promote it to an operator. Here we also have an operator, and this can be written as 1/2 integral from 0 to L dx. So here we could also write it in the following fashion: d phi hat dt squared plus d phi hat dx squared, like this. Now I'm interested in calculating the energy density of the vacuum. In particular, I want to consider this expectation value, so the expectation of the Hamiltonian in vacuum. So here we have the vacuum state, and here as well. And by considering the fact that the expectation of these operators, for example, A minus N, A plus M, one can show that this is equal to delta Mn. And why is that? Well, remember the fact that the commutator between An minus and Am plus, this is equal to delta Mn. So for example, you can take the expectation of both sides, and we assume that the inner product between the vacuum with itself is equal to 1. This vacuum state is normalized by assumption. And we also have to remember the fact that An minus acting on the vacuum is 0. For example, you can rewrite this as An minus Am plus equal to Am plus An minus plus delta Mn. And when you take the expectation here in the vacuum state, here you just have to multiply this by 1 because of this property. And this expression here gives 0 due to this. Therefore, you can show that indeed this equation here is true. And in a similar fashion, you can also show that the inner product between A hat M plus and A hat n plus this expectation is equal to 0. And in a similar fashion, if you put a minus here and a minus here, so if you consider a minus, and also if you consider a plus here and a minus here, you get 0. And this is quite obvious due to this property. That's this one here, because this state annihilates the vacuum. So why am I writing these expressions down? Well, when you take the inner product of this inner product here where you have the Hamiltonian there, you have to remember that in this expression the Hamiltonian can be written as an integral over phi dot squared and the derivative with respect to x of phi. And we have the expression for phi, and so we also have the expression for phi dot, which we called pi. And we can also calculate the expression of the derivative of phi with respect to x. And then we can take the expectation with respect to this vacuum state. And since these expressions are squared, you will have the products of two of these operators. And since we can calculate them, we can also calculate the expectation of the Hamiltonian. Now, in this case, I will skip the calculation because it's nothing difficult if you put all the pieces together, and you also have to carry out the integral, which can be performed because you will have to integrate over a certain sinusoidal function coming from the expression here. So when you square the derivative of phi, for example, with respect to t, you will also have squares of sinusoidal functions. And they can be integrated. So there is nothing difficult about that. When you do the calculation of this expectation, what you get is 1/2, and then you have a sum over n from 1 to infinity of omega sub n. Now we have to remember the fact that omega sub n is equal to n pi over L, and now let me define the 0-point energy per unit length between the plates, which we define as epsilon sub 0. This is just given by this inner product, so the expectation of the Hamiltonian divided by the length, so the distance between the two plates. So this is the energy per unit length, and it's just given by 1 over 2L summation over n omega sub n, and this can be written as pi over 2L squared summation over n from 1 to infinity of n. This is the expression, and of course, as it could be expected, the 0-point energy density epsilon sub 0 is divergent, and it must be first regularized and renormalized. A regularization means introducing an extra parameter, which is called the cutoff scale, into the theory in order to make the divergent quantity finite, unless that parameter is set either to 0 or infinity, depending on the concrete regularization procedure that has been used. Usually there exist different possible ways to regularize the divergent quantities. However, different regularization procedures lead to the same final physical results. After a regularization, one obtains an asymptotic expansion of the regularized divergent quantity at small or large values of the cutoff. This asymptotic expansion might contain divergent powers and logarithms of the cutoff scale, as well as finite terms. Then, renormalization gives a physical justification for removing the divergent terms and leaves us with the finite contributions responsible for the physical effects. Now we will apply the procedure to regularize this divergent series, And in particular, we define the quantity epsilon sub 0, which depends on L, and this expression depends on L, but we define also another parameter, alpha, in such a way that when alpha is small, we get back the divergent expression. So we define it to be pi over 2L squared summation over n from 1 to infinity n, and then we have the exponential of minus n alpha over L. And in particular, this can also be written as omega n alpha over pi if you want. So the exponential depends on this frequency, but also on alpha. So as alpha goes to 0, you can see that this exponential goes to 1, and therefore you get back the original expression. However, it is convenient to write it like this because this will help us identify exactly what the divergent terms would be, and it will be possible to separate the divergent part from the quote-unquote finite part. Now, this expression can be evaluated with some simple mathematical tricks. In particular, this can be written as minus pi over 2L. So notice that here I have L squared, and here I put L because the factor of L will appear when I take a derivative. So here I will rewrite the derivative with respect to alpha of the series over n from 1 to infinity of the exponential of minus n alpha over L. So with this derivative, I can get rid of this factor of n. And that's why it's useful, because now I can calculate the series and I can also take the derivative. So I will skip that part. Well, this is a simple geometric series because this can be written as the exponential of minus alpha over L to the power n. So we know how to sum a geometric series. This is a geometric series because its argument here is raised to the power n. And then you can also take the derivative. So I will skip that because it is quite standard. I have pi over 2L squared, so I will get back a factor of L squared there. And then I have the exponential of minus alpha over L, and this will be divided by 1 minus the exponential of minus alpha over L. This is squared. Now, this term here can also be rewritten in another fashion. For example, like this. You can check that if you divide both the numerator and the denominator by this term, you get pi over 2L squared. So here I have 1 divided by. When I divide by this, the denominator, and I put the term inside this parenthesis, I have to be careful because there is a square here, but this can be done. You can rewrite it as the exponential of alpha divided by 2L minus the exponential of alpha divided by 2L with a minus. So here you have a minus, and this is squared. And in this case, this is proportional. So what we have inside these square brackets is proportional to the hyperbolic sign. And we can rewrite it as pi over 8L squared. So this 8 comes from 2 multiplied by 4. So if I divide this by 2, I have exactly the hyperbolic sign. So since I have introduced this factor of 2, when we square it, we get a factor of 4, because that's inside these square brackets, and therefore I have to multiply this by 4 if I want to get rid of this factor of 2. So that's why I have this factor of 8, and here I have 1 over the hyperbolic sign squared of alpha over 2L, like this. Now it is possible to expand this ratio for small alpha. In particular, this can be expanded in a so-called Laurent series, and this can be done according to complex calculus. And in particular, if you want, you can also do the expansion starting from here if you prefer. It's not mandatory. For example, this one here is convenient because it can be expanded, for example, by using Wolfram alpha. So if you use a Wolfram alpha, you just Google Wolfram alpha and you expand such a term. If you want, you can expand this expression where the variable is called x, and Wolfram alpha will give you the expansion for small values of x, which is very similar to what we are doing here, except for the fact that x is this. And in our case, we're actually expanding over alpha because this is our variable and alpha must be small. But anyway, if you do the expansion, this will be equal to pi over 2 alpha squared minus pi divided by 24 L squared plus, and then you can write the rest as 1 over L squared, something of the order of alpha squared over L squared. So you can see that as alpha goes to 0, this term here will vanish because it will be proportional to alpha squared, and there are also higher order terms. There is a term that does not depend on alpha, it depends on L, and a term that diverges if alpha goes to 0. So the divergent part when alpha is small is this one here. And in particular, the crucial fact here is that the singular term does not depend on the distance L between the plates. And this can be interpreted as the energy density of the zero-point fluctuations in Minkowski spacetime without boundaries. So what I mean is that this term here, it's as if we're considering epsilon 0 of L alpha, and we calculate the limit as L goes to infinity of this expression. So remember that epsilon 0 is what we defined in here. So it's the 0-point energy if you want. And so it's as if the two plates are placed at an infinite distance between them. So in that case, we can say, okay, so in that case, there must be no force acting on the two plates. And we can set the overall energy when the two plates are so far from each other to 0. So in particular, we can redefine our energy as epsilon 0 of L alpha minus the limit as L goes to infinity of epsilon 0 L alpha. So in this case, we can get rid of this divergent term, and we can define this as delta epsilon 0. Now, at this point, if we consider the limit as alpha goes to 0, this energy here, this energy density does not diverge anymore, because you can see that we have got rid of this term, and when alpha goes to 0, since this term vanishes due to the fact that alpha is in the numerator here, this is just equal to minus pi over 24 L squared. And we can define this to be the renormalized delta epsilon. So let's call it delta epsilon ren as renormalized, REN if you want. And at this point, remember that this is the energy per unit length. So if we multiply by the length, this will give us an energy. And if we calculate the partial derivative with respect to the length, to the distance between the two plates, this would be proportional to a force, the force between the plates. In particular, the force will be minus this derivative, this partial derivative. So let's define it like this. With this minus, this is analogous to the fact that, for example, when you have a potential energy and you want to calculate, for example, the force along the x direction, you have to calculate the derivative with respect to x of the potential energy, where the potential energy is V here, and you also have a minus sign. Now, if you do this calculation by using this expression for delta epsilon renormalized, what you get, remember that you also have to multiply by L and then take the derivative, you have minus pi divided by 24 L squared. So this minus here, this negative sign, indicates the fact that the two plates are pulled towards each other. A similar calculation can also be done in four-dimensional space-time, which is a little bit more complicated because you have more degrees of freedom, but it can be done. For example, I did it in some lectures related to quantum field theory, but I will not get into the details here. And let me also tell you that it is possible to find other elegant and quicker ways to calculate the finite energy without resorting to this kind of regularization that I used here. One could start directly from this divergent sum and consider a generalization of this sum to the Riemann-Zeta function evaluated at -1. So in particular, the Riemann-Zeta function of x can be defined as a series, and this can be done only for x greater than 1, for real x's greater than 1. So the sum goes from 1 to infinity, 1 over n to the power x. As I said, it converges only if x is greater than 1. But this function can be analytically continued or extended to all complex x's except at x equal to 1, where the function has a pole. And I have discussed this in the course on complex calculus, for example, if you're interested in more details on that. But in this case, I just want to give you some hints, and in particular, since you can see that this series representation of the Riemann-Zeta function is true only for x greater than 1, we can neglect the fact that we can use it only for x greater than 1, and we can say, well, why don't we plug into this expression x equal to -1, right? So if you do that, 0 of -1, it's as if it can be written as a sum over n from 1 to infinity, where here you have 1 over n to the -1. But 1 over n to the -1, of course, is equal to n, like this. Well, this actually works in the sense that if we replace this divergent series with the 0 to the -1, we get the correct result, because 0 to the -1, if we do the so-called analytic continuation, and in that case we cannot really use this series, but we have to use the generalized expression for 0 to the -1, we get that this is equal to -1 over 12. This can be proved quite rigorously, actually very rigorously, but mathematically. So it's a mathematical proof where we can extend this, the domain in which this function is defined. So although this series here is divergent, it can be associated to a finite value, let's say. And similarly, this can be done also for other divergent series. And let me tell you that at first glance, this procedure might seem miraculous and lacking physical explanation of why we are neglecting these divergences, unlike the renormalization approach. However, it has been verified in many cases that the results obtained using the zero function method are in agreement with the more direct renormalization procedures. And it is also important to highlight the fact that the Casimir force has been verified experimentally, which pushes us to accepting the mathematics that comes from these somewhat complicated and seemingly non-rigorous calculations.